we have, so usually this is written, I'll write it in the form that's here, so it's x times cosine theta plus n cross x times sine theta plus n times n dot x times 1 minus cosine theta. That's the more standard form. So that should be, everything should work out. Let's just check. So the x dot n times n, that corresponds to this times 1. And then this times cosine with the negative here, that corresponds to this negative cosine here. So that works. And then the x cosine is this times this, and then this n cross x sine is this right here. So it's the same thing. And this can be written in, so we know all about n cross is the same as capital N times, right? So little n cross x is the same as skew symmetric matrix, capital N times x. And so when we work it all out, this can be written as the identity matrix plus sine theta times capital N plus 1 minus cosine theta times capital N squared, all times x. Okay, so if you work out the fact that n times x is little n cross x, and n squared times x is the same as the identity minus n transpose times x, and other little tricks like that. You can take what's written there and put it in this matrix form, where this matrix right here is the axis angle description of rotation. It may not be obvious up front that this is a rotation matrix, but actually we can check it right away. So we can check is R times its own transpose equal to the identity, and we can check that because we get the transpose of this is going to be I. So the transpose of the sum of things is the sum of the transposes. And so this is going to be I minus sine theta n plus 1 minus cosine theta n squared. This is the transpose. The reason why this is the transpose is because the transpose of this is just a negative n quantity squared. N transpose, so n squared transpose is the same as n transpose squared, which is the same as negative n squared, which is just n squared. So this term doesn't change, but this term does because the transpose of n is negative n. So that's why the sign changed. This is R transpose times identity plus sine theta n plus 1 minus cosine theta n squared. So I'm just checking to see if this works. And if and then if you multiply out all the terms, you get the identity, you get a negative sine theta n, and then you get a positive sine theta n over here, and negative sine theta n over here. Those cancel. This times this, and then this times this cancels because this sign is different. And then you get the final term is going to be plus 1 minus cosine theta n to the 4th power. Oh, but then this term here is going to be negative sine squared theta n squared. So that's all that will remain. Everything else cancels out when you complete the square, if I've kept track of things correctly. And so, this is squared too. Okay. Now, the thing about a skew symmetric matrix of this form is that you can show that n cubed is equal to n. That's not true for an arbitrary skew symmetric matrix, but because n dot n is equal to 1, you can show that it is true. And so what that means is that this n to the fourth can be written as n cubed times n, which is the same then as n squared from this fact up here. So then these two terms can be combined. So if we complete the square over here, what we have is 1 minus 2 cosine theta plus cosine squared theta. And over here, so things are not quite working out. Oh, let's see. Identity, sine theta, negative sine theta. Identity. We have another, we have this times this plus this times this. We have another term in here. So we have a 2 times 1 minus cosine theta n squared, right? It's the identity times this plus this times the identity, right? So, does that end up canceling then? Let's check. So we get 2 times 1 minus cosine theta from here. And then we have the stuff that we calculated already, plus 1 minus 2 cosine theta plus cosine squared theta minus sine squared theta. So what do we have here? We have 3 minus 2, so this is minus 4 cosine theta plus cosine squared theta minus sine squared theta. Well, that doesn't look good.
Should that be I times cos theta?
Say again? Which one? What did you draw the point? So
that was what it is.
yes.
So should this part be
Going way back to the beginning. No, so this is so if you pull everything out, you can write it in this form. So let's check again. So this is the axis angle formula. So let's see, so 1 minus, does somebody see a,
the photo, when n to the power 4,
yeah,
when it's converted to the n squared, it should be there should be a minus sign.
here,
No,
no?
for even for odd case, that's true. For even case, if it is n to the power 4,
Yeah.
and it can be converted to the power of 2, to the power 2
Uh-huh.
square. And there's a minus sign before the n squared.
If you have n to the power 4, that's equal to n to the power 3 times n. So either there should be a minus, a minus sign here, or if this is true, then this would just be n squared. So maybe this should be negative n, and then this should be negative n times n is negative n squared. Well, we can check that, because suppose I give you E3 cross, okay, so E1, E2, E3. So if I give you E3 cross E1, that should be equal to E2, right? And if I do this, now if I say E3 cross E3 cross E3 cross E1. So we can ask, what is that? And that would be the same as taking the skew-symmetric matrix E3 cubed times E1. So this is E3 cross E3 cross. So this one right here is E2. But E3 cross E2 is negative E1. Which is negative E3 cross E1. And E3, right, so if we look here, E3 cross E2 is going opposite direction, so it's negative E1. Then E3 cross E1 is again negative E2. So this, right, so the first statement right here, this is the same as the skew-symmetric matrix E3 times E1 is equal to E2. And if we do it 3 times, that's equal to negative E3 E1. So E3 cubed is equal to negative E3. Yes? So this, there should have been a negative sign here. Okay, so that changes things. So let's go back again. So let's do it from scratch. Okay, so we multiply through, we get the identity, we get sine theta, we get negative sine theta. We get this one over here, 1 minus cosine theta times n squared, and we get 2 of them. And then we get sine squared theta n squared. This times this, it's a negative. And then we get 1 minus cosine theta squared n to the 4th. Now is that everything? I think it is, because we have a 2, and the others don't have any cross terms, because it's this times this, and this times that. Okay, so does everybody agree with this? So now if we say that this is this, if we use this fact up here, then this is negative n squared. Okay, So now we complete the square over here. So what we have is basically identity plus n squared times, so this is 2 minus 2 cosine theta. This is negative sine squared theta. And then over here, we get negative the quantity 1 minus 2 cosine theta plus cosine squared theta. Okay, so this is going to be the same as plus, make this minus, plus, minus. We can get rid of these parentheses. Now, negative sine squared and negative cosine squared add to give negative 1. So this and this together are negative 1. And we have a 2, negative 1, negative 1, so those add together to give 0. And then we have this canceling with this. Now, why do we still have a 1 left? Why do we still have a 1 left?
It is 0.
It is 0? Did I forget to cancel? Okay, so let's do it again. So 2 minus cosine theta minus sine squared theta plus, so this is a minus 1 minus 2 cosine theta plus cosine squared theta. So then this is minus plus minus. So, okay, so this 2 canceled with this and this and this. I forgot to erase it. That's what we're saying, right? There's a 2 here also from here. This canceled with this. Okay, so this is 0. So this is a rotation. Actually, all I've shown is that it's orthogonal. It's more complicated than this to show that the determinant is equal to 1. But you can at least see when theta is equal to 0, this becomes the identity matrix. And the determinant of the identity matrix is equal to 1. And so this is the axis angle formula. And in the paper, that is actually used to describe rotations. And so what we have is that, and I'll say also that this can be described using the matrix exponential. We can use the matrix exponential you can show that this same matrix can be written as the exponential of theta times n. In other words, this is the identity plus theta n plus theta squared over 2n squared going all the way out. And if we use actually that same identity that I had before, that n cubed is equal to negative n, then you can collect terms in this infinite Taylor series, which is how the matrix exponential is defined. We can write this as identity plus all the terms that multiply n, plus all the terms that multiply n squared, and every higher term can be reduced back down to one of these two using this kind of formula. And what ends up being here and here are exactly what we have over here. So that's the axis angle formula. And that's important because given any rotation matrix, we can ask what is the axis of that rotation and what is the angle of that rotation. So if I give you some rotation r, and I ask what is the n and what is the theta from that rotation matrix, we can use this formula to write the, also I'm just repeating the formula. So that's R, and R transpose is the same thing except with a negative sine theta. And I can subtract one from the other, and I get R minus R transpose is equal to 2 sine theta times n. And remember, n is the skew-symmetric matrix that looks like this. It has embedded in it the entries of the vector little n. And so I can very easily find what little n is, because it's basically right here. All of the information about little n is in big N. But first I need to know what theta is. If I know what theta is, then I can, and if theta is not 0, so it makes sense to divide by theta, then I can easily find out what n is. But how do you find out what theta is? Well, we can take the trace of R, and the trace is the sum of the diagonal entries. Now, this matrix has a trace of 3. It's just 1 plus 1 plus 1, the diagonal entries of the matrix I. This matrix is skew-symmetric, so it has zeros on the diagonal. Its trace is 0. This matrix is going to be 1 minus cosine theta times the trace of n squared. So what is the trace of n squared? So let's work that out. So if I give you the matrix n times itself, that's 0, 0, 0, negative n3, n2, negative n1, n3, negative n2, n1, and I multiply it times itself. Then what do I get on the diagonal? That's all I really care about when talking about the trace. So on the diagonal, I'm going to get a negative n3 squared negative minus n2 squared up here. The next diagonal entry is going to be negative n3 squared minus n1 squared. And then the last one is going to be negative n2 squared minus n1 squared. And when I sum those up, what am I going to get? I'm going to get 2 occurrences of n3 squared, 2 occurrences of n2 squared, and 2 occurrences of n1 squared. But remember that we're talking about n being a unit vector, so n1 squared plus n2 squared plus n3 squared is equal to 1. So if I have 2 occurrences of each one, I'm going to get 2. So the trace of this matrix right here is equal to 2. okay, because n1 squared plus n2 squared plus n3 squared is equal to 1, and I have 2 copies of each. And so what I get is 3 plus, so this is, let's see here.
Should be -2.
Oh, right, -2, because these were all negative signs. Thank you, -2. So this is going to be 3 minus 2 times 1 minus cosine theta. So this is going to be, so 3 minus 2 is 1. 1, and then this comes through and it's going to be 2 cosine theta. And the reason I know that that is true is because if I look back at the matrix, the R3 of theta, which is cosine theta, negative sine theta, etc. And I take the trace of this, I get 2 cosines in 1 and the number 1. So I get the same answer. Okay? So, and actually, if you take any of those fundamental rotations, R1, R2, R3 of theta, you'll get the same answer. And in fact, for any rotation matrix, you'll get this answer. So what that means then is I have a very easy way to find what the angle theta is. So what we do is we restrict theta to the range from 0 to pi. And if you look at the function cosine in the range 0 to pi, this is pi, this is 0. The cosine of theta in that range is unique in the sense that you, the inverse function, you have one value. So you have one value going this way, and you have one value going this way. So what that means is that inverse cosine really means something in this range. If you go over the full range from 0 to 2 pi and say, what is inverse cosine? Well, you could be here or you could be there, right? But if we restrict theta to the range 0 to pi, then we can say that theta is equal to the trace of r minus 1 divided by 2 cos inverse. Right? That's just subtracting 1, dividing by 2, and taking cos inverse with theta in the range 0 to pi. Now, that provides a complete description. So any rotation can be described as a rotation by angle from 0 to pi around an axis n, where n can point anywhere on the unit sphere. Okay? And you can describe any rotation in this way. You can restrict theta to that range, and you can make n point anywhere on the unit sphere. Alternatively, sometimes people like to keep theta in the range 0 to 2 pi, and then restrict the range of the vector n to a hemisphere. But if you allow n to go over the whole sphere, and you let theta go from 0 to 2 pi, then you have a redundant description of rotation, meaning if you take n going to negative n and theta going to 2 pi minus theta, it's the same rotation. So to avoid redundancies like that, we keep theta in this range, and we allow n to be in the unit sphere. And so when we do that, we can uniquely recover theta just by this formula. You give me a rotation matrix, I take its trace minus identity divided by 2, type inverse cosine, that gives you the theta, the angle of the rotation. Once you have the angle of the rotation, you can come back over here, take R minus R transpose, that's going to be a skew-symmetric matrix, divide that skew-symmetric matrix, which means divide every entry in the skew-symmetric matrix by 2 cosine theta, where the theta is what you got from over here, and then that gives you your n, and from your n, you can get the little n, okay, the axis. So given a rotation matrix, you can easily calculate what the axis and the angle of that rotation matrix is. And so that's the axis angle description of rotations. So that's one part of the background that you need for this paper. The other part of the background, I'm not going to finish today, so we're not going to actually get to the details of the paper today. But the second part is the idea of Jacobian iterations. And so I'll just motivate that, actually, and it's easier to motivate it with a robotics example than a spacecraft example. So we'll talk briefly about Jacobian iterations today, and then next time we'll take these two pieces and put them together to fully understand that paper. So Jacobian iterations. Okay, so in general, if you have a nonlinear problem, like you want to, you have an equation that you want to solve, like x equals f of, let's say, f of q. Okay, where this is some nonlinear function. And you're given x. And you want to find what is the q that solves this equation. Okay? How do you do it? Well, maybe you go to Mathematica and you put in the solve function, right? But, you know, we want to know how to do it ourselves, because, you know, sometimes you don't know what's going on inside the box. And so one kind of problem like this is I have an orientation of my satellite, and I want to find out what the flipper angles should be for my microsatellite, right? That's one kind of problem of this sort, where in one shot, can I do, if I turn my flipper angles, can I get